All right. It is now recording, so whatever you say will be logged on YouTube forever and ever. All right. This is your final exam boot camp. We will be going over test 1, version 1, test 2, version 2, test 3, version 3 of Chem 2535 of the year 2023. You are highly suggested to drink water throughout this, as I will be drinking water. It might be in weird glasses, but you are highly encouraged to drink water throughout this. But with that being said, we shall go ahead and get into it. I'm going to go ahead and share it to my iPad, the good old trusty iPad. All righty, let's make this horizontal so that the people watching on YouTube have an easier time. If you have a question in the chat, I'm sorry, that's a lot for me to handle. Gavin may pop up in here sometime. If not, that's okay. So if you do have a question, throw it out in the mic. Like I said, if you ask a conceptual question like R versus S, sorry, I'm going to skip over that. But if you want me to repeat something or like briefly explain this again or quickly why this happens, sure, go for it. So I'm going to make sure you guys can see the screen. Can I get a thumbs up from you guys if you can see my screen? Thumbs up. All right, I got some thumbs up. Great. So for test 1, version 1, we're going to start off really easy. So a cool thing about looking back in test 1, you guys can look back in the nomenclature, and if you look back at your exam, you feel really bad, like, oh my God, how did I get that wrong? Because you're so good at nomenclature. I definitely had that happen to me. Test 1, semester 1 was my lowest grade, and the mistakes I made on this nomenclature, I felt so dumb. But don't worry, it's comeback season, right? So the biggest thing that a lot of people do when they look at this is straight up count your longest carbon chain right across. The thing is, that usually works, but another thing you have to look at is, can you make the carbon chain longer? What I usually do is I look at the left and right two most carbons. Two most, that's a scientific term, totally. Yeah. But let's see if we can expand it a little bit. And wouldn't you know, both of these, we can expand it. If we went up here in this direction, we can actually expand the carbon chain by 2. We can expand the carbon chain by 2 instead of 1 in both these situations. So if I were to redraw this or re-highlight this, this would be my longest carbon chain. If I count it, it would be 1. Here, let's count it. 1, 2, 3, 4, 5, 6, 7, 8. It would be an octane. Now I numbered it left to right, but let's number it right to left. 1, 2, 3, 4, 5, 6, 7, 8. So I know my parent chain is first off octane, right? If it's octane, let's look at our groups. Right now we have a trimethyl. The only functional groups we have are methyl groups. We have 1, 2, 3, 4, and 7 going right to left. Let's make this pink. From left to right, we would have 3, 5, 6. Now, you want to be inclined, well, 3, 5, and 6, it looks like it's a lot lower. Or if you added them up, they would be the same. But we have to look at the first point of difference. 3 and 3, same. But for the top one, we get the lowest number first in that top numbering scheme. So 3, 4, and 7 is our preferred numbering, specifically because of that 1 point. Any number before that, or not before that, after that, is totally irrelevant. If you have a numbering scheme of like 1, 2, 6, 6, but another numbering scheme would have 1, 2, I don't know, 12, 12. Don't think about it too much. I don't think that would work out. 1, 3, 1, 3, 12, 12. The 2, 6, 6 would work out because that 2 is lower. Now, looking back at it, that did not check out, but we'll...
3, 4.
Yeah. Here, let's draw it out. If we had 1, 1, 12. But if we had 1, 12, nah, that wouldn't work. I'm trying to think of a good example for you guys. 1, 1, let's do... That's too much work. Let's just keep going with it. You guys will see it as we go along.
Shouldn't
it be 3, 4, 6?
3, 4, 6. Did I count that wrong? 3, 4, 6. Yeah. Good catch, you guys. 3, 4, 6, trimethyl octane. Just to be real clear, commas only go between numbers. Dashes only go between numbers and letters. If you have two letters together, there is nothing there. All right. Let's go for this next one. We have 1, 2, 3, 4, 5, 6 straight across. But if you look at the left two most carbons and the right two most carbons, we can expand the carbon chain to 7 and 8. Let's count on the right side, right to left. 1, 2, 3, 4, 5, 6, 7, 8. We have, for the blue numbering scheme, 3, 6. For the left to right, we have 3, 6. 3, 6 both ways. And our carbon parent is going to be octane. Now, if we have a tie for numbering, what is our tiebreaker?
Alphabetical.
Yep, alphabetical. All right. So alphabetical, which one would get the priority? Bromine, B. So it would be 3 bromo. Whoops. 6 methyl octane. All right, let's go to the third one. Again, straight across. A lot of people would do this, but let's look at the left and right two most carbons, see if we can expand it. In actuality, for this right one, we can't expand it beyond that oxygen because that's an ether group. And if we were to number it this way, it's the same thing. It's that carbon right here in the corner, right here, that's achiral. So same thing, we'll just count it across. It's a butane. Now it's a butane, we have a 1, 2, 3, 4. We have a 2, 2, and a 4. Right to left, 1, 2, 3, 4. We have a 1, 3, 3. Perfect example of what I was trying to show above. A lot better than me pulling it out of my ass. All right, you have 2, 2, 4 and 1, 3, 3. You might be inclined to pick 2, 2, 4 over the 1, 3, 3, but if you look at that first point of difference, 1 and 2, 1 obviously beats 2. Oh, excuse me. You don't have to look at the rest of the numbers beyond that. All right. Automatically, because 1 beats 2, that's your numbering scheme. So it's going to be, oops. There it is. 1 methoxy, 3, 3 dimethyl butane. All right. Let's count across again. Pentane. If we look at the left and right two most carbons, we can't expand it. All right. So we won't worry about that. It's a pentane. We know that it's a pentane. Count from left to right. 1, 2, 3, 4, 5. Right to left. 1, 2, 3, 4, 5. Now the thing to note, we have a functional group. Functional group is going to be alcohol. The functional groups that you are responsible for knowing are alcohols, amines, alkenes, and alkynes. The priority group goes as follows. Alcohol, amine, alkene and alkynes are tied, but if you have to choose between the two, it would be alkene. But both ways, it would denote the alcohol as 3. So let's look at the numbering scheme as a whole. Left to right, it would be 2, 3, 4. Right to left, 2, 3, 4. Again, we have a tie. What is our tiebreaker? Alphabetical order. So if we had to choose between bromine and chlorine, we would choose bromine. So bromine, we get the 2. It would be 2 bromo, 4, I almost said methyl, chloro, pentan, 1 all. You can write it as pentanol, not 1 all, oops, 3 all. If it was a 1, you are welcome to not write the 1, just do pentanol. But honestly, I would just keep the 1 there just in case. Yeah, it's stupid. All right, now we have some of the trickier ones. We have some functional groups and we have cyclic structures. For cyclic structures, an easy guess is the first carbon for your cyclic structure is always going to be one of your priority groups. If not a priority group, somewhere with the most amount of branches, all right? Alkene takes priority over alkene if you have to choose. Yes, that's right. So one of the tricky questions we had last year was a cyclohexane that looked like this. CH3, CH, BR, BR. Something along the lines of this. A lot of people counted 1, 2, 3, and 4. And I would get that. I understand, because like if you're starting at a branch, you want to go in the direction of the other branches because that would minimize the numbers. And that makes sense. Additionally, the bromines make it a lot more enticing because you get the lower numbers for the bromines. The thing is, if you were to look at the numbering, this numbering that I did in blue would be 1, 2, 4, 4. But if you did it this way, 1, 2, 3, 4, 1, 1, 3, 4, this one would win because of that difference. The pink numbering scheme would win. You want the most amount of branches because it gives you the lowest numbers total. Even though it might not look that way, it's best to just write out the numbers. So with this in mind, here, if you guys need to write this, I'll just move this to the side for now, but I'm going to keep moving forward, okay? If I were to count this, I would go 1, 2, 3, 4, 5, 6, or 1, 2, 3, 4, 5, 6. Now, you might be asking, why am I doing that? Well, first off, again, when you're counting in a cyclic structure, you want to start with a branch, preferably something with a functional group. But this one doesn't have any functional groups. Next, you want to count in the direction of the next branch. So I know if I started at like fluorine, for example, I have to count in the direction towards the bromine to get the lowest number. And if we look at this, the numbering scheme would be symmetrical. I'm not saying the compound is symmetrical, but I'm saying the numbering scheme would be symmetrical. So I know in advance, if I were to draw all 4 different numbering schemes, I would obviously choose the tiebreakers that gives me bromine as the lowest numbering scheme. So the 2 I did give you the 2 out of the 4 possible numbering schemes that are preferable. The 2 numbering schemes I just did give bromines the lowest numbering because of alphabetical. But as you can see, both the pink and the blue give bromine 1 and 4. 1, 2, 4, 5. 1, 2, 4, 5. So how do I look at this? You have to look at the next layer of tiebreaker. Which one gives me the lowest numbering for the next lowest alphabetical? And that would be chlorine. All right, chlorine would get 2. Chlorine would get 2 in the pink numbering scheme. Chlorine would get 5 in the blue numbering scheme. So I want chlorine to get number 2 because, again, a second alphabetical tiebreaker. A little beyond what we taught you, but it's that concept we're trying to ingrain for alphabetical being a tiebreaker. So we would number it as 1, 4, dibromo, 2, chloro, 5, methyl. We move this down and add that dash that I forgot to put. Here, let's just do that. 5, methyl. Important to remember that cyclohexane. Now, let's count across. A lot of people might do this. The thing is, you can't do that because you're going over a different atom. Oops. You're going over a different atom. Nitrogen here is not part of that carbon chain. The longest carbon chain that you'd have is going to be a butane right here. And if I look at the left and right most carbons, we cannot extend it. So now let's look beyond that. So I have branches at that first carbon, first and third carbon. If I counted the other way around, it'd be 1, 2, 3, and 4. So the black numbering would be 1 and 3. The right numbering, right to left, would be 2 and 4. Now, you might write this out, but you actually didn't need this at all because look at this. We have an amine group. This amine group takes priority no matter what. No matter what the numbering scheme is, this functional group has to get the lowest number possible. So the black numbering scheme, left to right, is automatically going to be that numbering scheme, all right? So if you're going left to right, we have a butane, a 3-bromo, and then we have a 1 amine. Now, we also have a methyl group right here. How do we denote that? Because that's still a branch, but it is attached to the nitrogen. So we would give it the denotation of N. So in actuality, we would have 3-bromo, Oops. N-methyl butan 1-amine. Again, like the alcohol, you're welcome to drop the 1, but personally, I wouldn't. When in doubt, don't leave it out, okay? If you had a dimethyl, it would be N, N dimethyl. Again, this doesn't apply to this compound, but just in case you had to see it again on the final. Again, you have a cyclic structure, but hey, look, you have functional groups. Well, that automatically gives you, all right, this is where your first carbon is going to be. Now, you might be thinking, well, where is the direction you're going to go? And which carbon are you going to start at? Because oxygen, alcohol, and nitrogen in the amine group are both present. If they're both present, the alcohol takes priority. So this is automatically carbon number 1. You can go clockwise, 1, 2, 3, 4, 5, or counterclockwise, 1, 2, 3, 4, 5. Which numbering scheme do we want? Right? Now, a lot of people think you want to go counterclockwise, the pink numbering, because of the the priority. You might think that amine takes priority over chlorine. No, the thing is that we want to get across is that once alcohol takes priority, the amine group demotes to the level of branch status. It is no different than chlorine. All right. Even though it is a priority group, it's demoted to branch status because another alcohol is there. But the thing is, it still takes priority because when the prefix is applied to that branch status, amine, A comes before C in chloro. So amine still gets the lowest number, not because of the functional group, but because it takes alphabetical priority in that tie. Why doesn't the N come before the 3? N doesn't come before the 3 because we base off the alphabetical on the branch we use. If it was N-bromo 3-methyl, that would be different. Yeah, then the N and the 3 would be switched. All right, let's move forward. So we know that for clockwise, it would be 1, 3, 4. Counterclockwise, it would be 1, 3, 4. Alcohol is given that first priority, easy peasy. But again, in the counterclockwise, NH2 gets this, NH2 gets this in the clockwise. Again, we want to choose the bottom one, not because amine is a priority group, because again, it's a branch status group, but because A comes before C. It would be 3 amino, 4 chloro, cyclo, pentan, 1 all. If you got this right in the test because of the other reason, you got lucky. Whoops. Yes, there we go. All right. Now I finished nomenclature. What is the degree of unsaturation? All right. This, you straight up have to know the equation. C minus H over 2 minus halogens over 2 plus N over 2 plus 1. Right off the dome. Boom. Right off the dome. 17 minus 30 divided by 2 minus 0 divided by 2 plus 0 divided by 2 plus 1. Whoops. There we go. It would be 17 minus 15 plus 1. That would be 3. Hopefully you know that. Right. Which of the following molecule? For the following molecule, circle the most acidic proton. If you remember, acidic protons are going to be on halogens, oxygen, and nitrogen. All right. They can be on carbons, but we'll deal with that a little bit later. But for now, when they ask you this question, it's most likely going to be on a nitrogen or an oxygen. Why is it 3-amine? Was it 3-amine or 4-amine? 3-amine. Yeah. Okay. Even though these protons could be acidic, remember that pKa for an alkane is going to be around 50 to 60. While a proton on nitrogen or oxygen are going to be a lot more acidic. So for this kind of question, I would just mainly focus on the protons on an oxygen or nitrogen. All right, and then you just use the following rules that we talked about in the review session for test 1. So we look at oxygen and nitrogen. We look at the protons. Oxygen has no protons. Nitrogen has 1 proton. It's the most acidic proton. All the other protons are on an alkane or on a carbon, and that pK is going to be like 50. Excuse me. Ooh, that one also tasted like beer. Oof, I should not have started with beer. I mean, wheat water. My bad to the recording. All right.
I had a question.
Yeah.
So if instead of like the 4 like electrons on the oxygen, if there was like 2 hydrogens, would those 2 protons be like the same acidity and those would both like tie?
Mm-hmm.
Okay.
We had
Thank you.
O's there, or not O's, H's there. These would be more acidic. These would be more acidic. And they
Okay.
would die. Yeah,
All right. Thank you.
of course. That's not the case. Hold on. Let me reset. SiCl4, polar or non-polar? Well, if you know, Cl, Si, Cl, Cl, tetrachlorosilicon. That's going to be non-polar. Even though chlorine is electronegative, all of those 4 vectors point in opposite directions. There is symmetry among all of them. Another practice MCAT question I had was a lot similar to this. Which of the following molecules has the same molecular structure as methane? And this one was the answer. It's really easy. Gotta love Gen Chem, right? All right. Which of the following is the highest boiling point? When it comes to boiling point and freezing point, it comes to intermolecular forces. You learned that in Gen Chem. For the intermolecular forces, if you remember, hydrogen bonding is the strongest. Wait. Ionic bonding is strong for intramolecular. Electrostatic bonding, I think, is for different molecules. But anyway, for the scope of organic chemistry, the gold standard is going to be hydrogen bonding. Next is going to be dipole, and then van der Waals. Okay? So the highest boiling point will have the strongest intermolecular forces because it's going to take a lot more energy to break those hydrogen bonds, right? So we already know this pentane is not going to be it. It only has van der Waals. If you know, oils have a very low boiling point. But if you have this butanamine, that has hydrogen bonding. Hydrogen bonding occurs when H is attached to oxygen, nitrogen, or, I almost said phosphorus, fluorine. I almost said phosphorus. Either one of those, and you're going to have hydrogen bonding. So we know that this has hydrogen bonding. This is the answer. All right. Now, this type of question is very important. If you were to review anything for this test on top of this video, I'll review this type of question, the different types of versions for test 1. The strains. List all the types of strains in the following conformation. Some neato things, planar cyclopentane, that's going to have no bond angle strain. You're going to write all 3 out. Bond angle strain, torsional strain, steric strain. Bond angle strain does not exist when you have a planar cyclopentane or a chair conformation cyclohexane. All right, I'm going to repeat that. Bond angle strain doesn't exist when you have a planar cyclopentane or a chair conformation cyclohexane. All right, when you have a planar cyclohexane, there is bond angle strain, something we talked about in lecture, and you will see for yourself if you build the model set and try to force it to be planar. It wants to be a chair conformation. So because this is one of our 2 main hydrocarbons that don't have a bond angle strain, there is no bond angle strain. Torsional strain. Does it have a methyl group in a axial position? So remember, the 3 types of torsional strain we have are gauche, 1,3-diaxial, or flagpole. Flagpole only exists when you have a bow conformation. 1,3-diaxial is if you have a chair conformation with a methyl group in an or above, methyl group or larger, in a axial position. And what's it? Flagpole, 1,3-diaxial, and then gauche is when you have staggered conformation or eclipse, but you have 2 methyl groups that are close to each other in terms of like that angle. Okay. Torsional strain, we don't have any methyl branches, so we don't have any of that. Actually, wait, no, not,
Patrick.
I meant steric strain. My bad. Torsional strain happens when you have a Newman projection, but everything is eclipsed. And this always happens when you have a planar molecule. When a molecule is planar, all of those Newman projections are going to be eclipsed. All right. So if you have a planar molecule, automatically you're going to have torsional strain. All right. Yes. Eclipsed planar molecules. Now maybe think, well, that's pretty broad. If bond angle strain doesn't exist for planar cyclopentane or chair conformation cyclohexane, torsional strains for everything planar, and steric strain is pretty tough to beat. What kind of molecule doesn't have any of these? The answer would be, why not you take a chair conformation cyclohexane? Chair conformation cyclohexane does not have any methyl groups, and it's in chair conformation, and it's in a chair conformation for answering that bond angle strain. Strain. Yeah. All right. Now, question 7 asks you to list all types of steric strain in the following conformation. All right. So it tells you, all right, ignore your bond angle, ignore your torsional strain. Let's just focus on steric strain. You have the 3 types: gauche, flagpole, and 1,3 diaxial. Gauche, you need 2 methyl groups to be right next to each other and close to each other in that Newman projection. We don't have 2 methyl groups. We only have 1 methyl group. We don't need that. Flagpole, we don't have a boat conformation. Automatically, nuh-uh. All right. Now for 1,3 diaxial, do we have a methyl or any kind of alkyl group in an axial position? Yes, we do. So the only type of strain we have is 1,3 diaxial. If you had a chair conformation with an equatorial CH3, as another example, you don't have steric strain, you don't have torsional strain, and you don't have bond angle strain. Another example of no strain. Yeah. All right. Now let's look at the equilibria. The main thing to note, addressing a problem we saw in the problem set, is an acid must react with a base. All right. 99.9999% of the time on the test is going to shift left or right. Is usually not going to be true equilibrium. All right. The only time it's going to be true equilibrium is if you have 2 acid components that have the same pKa, which he's not going to do. It's Dr. Berg we're talking about. Come on. So let's identify our acid components. HF is a weak acid. H2O can be a weak acid or a weak base. But if we were to note HF first, that would be a weak acid. Now, that means F minus would be the conjugate base. And if we know, well, hey, an acid must react with base. So we know that water in this situation must act as a base. It accepts the proton if we're using the Bronsted-Lowry definition, which it does, and it becomes a conjugate acid, H3O plus, conjugate acid. Okay, if it becomes a conjugate acid H3O plus, we have a pKa of negative 1.74. That's pretty good. While HF has a pKa of 3.2. So again, some of you might think it's true equilibrium because you might apply that pKa to both the acid and the base components. You might put that 3.2 here as well. That's a bad 3. I think I was trying to draw 2. 3.2 here as well. And then negative 1.74 on the other side. That's not the case. pKa only applies to your acid. So these are the only 2 species you have to worry about. And the smallest or the lowest number pKa will dissociate the most. So if this dissociates the most, it's going to go this way. And it would be left. Now, this is a very beautiful question. The strongest acid or the strongest base? I am extremely confident this kind of question will show up on your final. Very, very confident. I know for a fact it's going to show up at least on one of the versions. Now, for this, you're mainly looking at your acid properties. All right, what makes it more acidic? Electronegative atoms. If you're going to have something comparing to like an a hydrogen on an oxygen, nitrogen, or a carbon, which one's going to be more acidic? The one in the oxygen, because out of the three, it's the most electronegative. Next is going to be which one has the most resonance structures, which one has the most inductive effect, which one has the largest electronegative atom, right? If you want more elaboration on it, refer back to the test one review session. I talked pretty in depth about it. But I'm going to show you the quick way of doing this on how I did it. All right. The thing to know, well, carboxylic acids have a pKa of 5. Alcohols have a pKa of around 15. With me knowing that, I already know this one and this one are not it. Because I already know carboxylic acids are more acidic than an alcohol. And we know this for sure because, hey, for all 5 of these situations, hydrogen is on an oxygen. But the 3 that I didn't cross out have resonance structures. If you were to remove that H, that conjugate base, the negative charge of the lone pair in that oxygen can resonate and door hinge on the other oxygen. It's stabilized by resonance. So now let's look at the difference between the 3. Well, these 3 have the same base carbon structure. They will when you're comparing them. So let's look at the inductive effect. Well, these 2 have electronegative atoms on a distant carbon that's pulling electronegativity away from that oxygen. That helps in acidity. The more electron density pulling away from the acidic proton, the more acidic it is. So I know it's not going to be this one because these have these happy-go-lucky functional groups. Now, they have to decide, well, hey, let's look at the location. Which one's closer? They're both the same location. Let's look at which one's more electronegative. Which one's more electronegative? Chlorine. So we know out of all 3 of these carboxylic acids, this one's the more acidic one because we have the closest halogen that does exist in there, in that compound, and it's the most electronegative one. Now, this one's a relatively tough question. Is this compound correctly named? I'll give you a hint. Normally, we like to avoid branch of a branch naming. So this naming, we taught you branch of a branch. If you can avoid it, that's what we like to do. All right. For this case, we see obviously a butyl group here. Let's see if it's right. Well, if we were to make this carbon chain left to right, easy, we have an octane with a propanil. First off, there are 2 things that are wrong. This branch of a branch would be butan 2-il. Not 1-methyl-propan 1-il. It would be butan 2-il. But I don't even think about that because if I were to look at the carbon chain, 1, 2, 3, 4, 5, 6, 7, 8, octane, if I went down, that would be an octane as well, but no branch of a branch. If I went down this way, it would be an octane with a methyl and a propyl group. That's preferable because we want to avoid branch of a branch. So we don't like that. They suck. I hate naming branches of branches. All my homies hate branch of branches, except Gavin. Gavin loves branch of branches. Right, Gavin? Are you here, Gavin? Yeah. That's okay. He's not here. But anyway, how I would name it is going down here where you have a methoxy group, a propyl group, and a methyl group. It's easier. You don't have the branch of a branch. And even then, if you did do that, the branch of a branch names are wrong. So this one is double dipshit. We don't like that. No, not another branch of a branch. Yeah, it sucks. But hey, they're making it easy on us. They're making it easier on us. We have a main chain that we don't have to worry about. We just have to name the branch of a branch. So let's identify the longest carbon chain. 1, 2, 3. We can go further. 4, 5, 6. That accounts for all the carbons. We don't have another branch. So we would know that it's a hexanyl. Now we just have to identify which carbon on that hexanyl is attached. It would be the 3rd one. Now, if you counted right to left this way, it would be 4. But again, we want the lowest number. So it would be 3. Hexan 3-il. Now, Patrick, what if you had, I don't know, a bromine here? Well, then if you had a branch, you would just name it more normally as if it was, a normal IUPAC name. You would be like 2-bromo, hexane, 3-il. Oops. That. But again, that bromine doesn't exist. Don't worry about it. Name the following bicyclic compound using IUPAC rules. Bicyclic, something else that you do have to know and don't really like, but hey, you have to name it. All right. For bicyclic, you have to first look at your bridgehead carbons. Bridgehead carbons, this one and this one. The thing is, you have to count as well the number of carbons between each of those bridgehead carbons. Well, for this one, we have 1. Let me just do it this way. 1, 2, 3. 1, 2, 3. And then we have 0. So if you look at our parent chain would be bicyclo, 3, that would not be a comma, 3, 0, because again, those are the number of carbons between each. Now let's count it. We have 1, 2, 3, 4, 5, 6, 7, 8. Be an octane, bicyclooctane. This is our parent. Now let's identify the branches. When we're identifying the branches, how do we number it? We number it by counting around the largest ring first. Even if the smaller ring has a fuck ton of branches or a functional group like alcohol or amine, you still have to count around the largest ring, no matter what. Fortunately for us, for this one, both rings are the same size, right? If it was 5,3,0, then we would have to go around the carbon with the 5 plus 2, the 7-membered ring. But for this one, we can go either way. So starting at the bridgehead carbon, I would probably go this way. 1, 2, 3, 4, 5, 6, 7, 8. Why am I going that way? Because I'm giving alcohol the lowest priority. Again, if I had to choose between the rings, I want the one with the alcohol. If I went the other way, 1, 2, 3, 4, 5, 6, 7, 8. Which one would win, 6 or 8? It would be 6. So it would be 6-methyl bicyclooctane. Let's erase that E. Octane 2 all, not 2, 3. My bad. 3 all. There you go. All right, let's move on. What is the approximate C5, C6 bond length? C5 and C6, that is a normal sigma bond. Sigma bond has a length of 1.5 angstroms. You have to know that. For a double bond, it's 1.3. Triple bond is 1.2. I think that's right. Someone want to fact check me on that? Whew. Is it 1.3? 1.33, 1.2. I think that's right. Pretty sure. All right. Hybridization
It's
of
1.54.
1.5. What is it? 1.44 or 1.33?
1.1.
What was it? Is it 3.3 or 4.4 for the double bond?
I think it's 1.4.
1.4. 1.44 for the double bond, 1.3 for the triple bond. I had the pattern right, but I got the numbers wrong. That was my bad. Yeah, 1.44 for the double bond.
Wait, Patrick, actually, it's 1.33. My bad.
I was right?
Yeah, you were right.
Ah, nut. You guys, that's okay. I've been gaslighting you guys so much throughout the entire semester. I deserve this. Yeah, okay. I was right. 1.5 to 1.55 for the single bond, 1.33, then 1.2. Okay, I had it. Okay, carbon 6. It's really easy, sp2. You have 3 electron groups. If you don't know that, sorry. You should retake Gen Chem. Okay. Hybridization of oxygen 1. Well, you might think, hey, 2 electron groups, it would be sp. Don't forget you have lone pairs. So there's 4 electron groups. That would be sp3. There you go. Now, carbon 2, what is that bond angle? It might look like 180 degrees, but you know that carbon 2 is sp2 hybridized. When a carbon has a double bond and 2 single bonds, it's sp2 hybridized. Excuse me. sp2, that's going to be a bond angle of 120 degrees. Now for carbon number 3, that is sp3 hybridized. Carbon number 3 is sp3 hybridized. It has 4 different electron groups. That would be 109.5. There are no lone pairs, so I'm not going to put a less than there. There's no lone pairs. What is the degree of unsaturation? What you can do is count all the carbons and the hydrogens and the oxygens and the nitrogens, put them in the formula. Oxygen is not a role in that formula, thankfully, but you would plug and chug. Or you can count the double bonds and you can count the ring structures. It's the easiest way to do it. I see 1 double bond, 2 double bond right here. 2. Classify C4 as primary, secondary, tertiary, quaternary. Erase all of this. And let's analyze carbon 4. All right. Primary, secondary, tertiary, quaternary. Hopefully, you guys know that it's secondary after the hell you went through for test number 3. Hopefully, you know that. If you don't know that, it's connected to 1, 2 carbons. There you go.
Could you go over the 120 bond angle again?
Sure, yeah. 120 strictly because carbon 2 is sp2 hybridized. sp2 hybridized is always going to be 120 degrees. Carbon that looks like this, that's always going to be 120 degrees. In contrast, if you had something like a lone pair there, which would be hella unstable, but throw me a bone here. If this was existent, that would be less than 120, because if you remember from Gen Chem, lone pairs take up a little more space, so it pushes this bond angle a little more. But thankfully, carbon 2 has no lone pairs. It is just the 3 electron groups. It's 120 degrees. List all the non-hydrogen atoms that must lie on the same plane as C7. Put your answer below. All right, let's look at C7. C7, sp2 hybridized, is on the same plane as C9, C6, C8. Everything it's attached to must be on the same plane. Now let's take a look. All right. Right, C7. Okay, yeah. Oh, oops, I was reading it as all the hydrogen atoms, all the non-hydrogen atoms. Okay. All right, C6. It is also sp2 hybridized. Everything is still planar. C5 is also existent. All of these hydrogens here on the side, not on the same plane, but it's not asking about the hydrogens. All right. Now let's keep going down the line. C5. C5 is sp3 hybridized. Even though it's on the same plane as C5, or not C5, C6, C7, C8, C9, even though it's on the same plane, everything it's connected to is not on the same plane because it's sp3 hybridized. So the atom that's connected to C6 still on the same plane because it's planar, because C6 is planar, but C5, tetrahedral, everything's attached to a different plane. So it would be C5, C6, C7, C8, C9. There you go. Now this one is relatively easy compared to what, again, the hell you guys went through in the subsequent test 2. All right, same, different, constitutional isomer or stereoisomer. Well, let's take a look. We have a compound right here and compound right here. Same molecular formula. If you counted it, they would be the same. If you notice, hey, if we just move this, kink it on over here, it would look the same, right? Well, let's double check. We have a 1, 2, 3, 4. We have a 2,3 dimethyl butane. 1, 2, 3, 4. We also have a 2, 3 dimethyl butane. They are the same. This was also really easy. If you were to count the carbons and the hydrogens, they would have the same molecular formula. And if you note, they also have the same degree of unsaturation. Degree of unsaturation is the Number of rings or the number of double bonds. Each of them have a degree of unsaturation of 1. But we know, hey, all of these carbons and hydrogens are attached differently. This is going to be a constitutional isomer. Same molecular formula, different connectivity. Now this one's a little tough. What are these? Well, hey, let's take a look. Let's color code these. Carbon front will be pink. Carbon back will be blue. All right. Hard to do pink carbon here. Blue carbon in the back. The back carbon right here is connected to CH3 and Br. I'm trying to do a seesaw configuration. Let me make this a little neater. Carbon front is connected to a methyl group. H. Right? If I were to redraw this, it would be C. My head carbons, CH3, Br, CH3, HHH. There you go. For this right one, let's keep it consistent with the colors. Carbon here, blue carbon here. Back carbon, CH3, HH. Front carbon, CH3, Br, H. Could redraw it? Hey, look. CH3, HH, Br, CH3, H. Well, if you look at that, look, they're the same. They're both 2-bromobutane. They're both 2-bromobutane. These are the same. These newer projections can get a little tricky. I have a strong feeling that he might recycle this kind of question on at least one of the copies of the exam, but this is a very good question to reflect on. You have a newer projection, but I would honestly use that projection, draw out the full carbon chain, and compare them. All right, now let's look at this. If I were to draw these as cyclohexanes, this one would be up, up, and up. You would have this. All of them are up. Now we have down, down, up. We would have down, down, and up. Hey, look at this. These are not the same. They are special. They have different spatial arrangement. Same connectivity. These are stereoisomers. Now, what kind of stereoisomer? Are they going to be enantiomers or diisomers? Even though the correct answer is stereoisomer for this test, if this was a test 2 question, the correct answer would be a diastereomer. There you go. All right. Now let's take a look here. All right. You have a one, two, three, then 2 methyl groups. 1 carbon, 2 carbon. That's the 2 here. 3 carbon here. 4 carbon here. 5 carbon here. Now here we have 1, 2, 3, 4, 5, 6. Automatically different molecular formula. These are different. Great. Oh, sweet. Final page of test 1. Good job, you guys. Okay, 3,3-dimethylhexane. So this is the highest energy conformation right here. If I were to draw 3 different eclipse conformations, I would make it really easy on myself. How? By keeping the back carbon the way it is. You see the back carbon has ethyl group here, hydrogen, and hydrogen. So if I were to repeat that here, let me color code it. This is what I'm talking about. CH2, CH3, HH, CH2, CH3, HH, CH2, CH3, H. Now, all we have to do for this front part, this front carbon, each different conformations we have in those bottom three, we're rotating that front carbon, this one right here. So for this front one, let's do it as CH2, CH3, and then we have the two methyl groups here. Now let's take that first conformation and rotate everything on that it's written in pink, the front carbon, rotate that front carbon. CH2, CH3, CH3, CH3. Let's rotate it again. CH2, CH3, CH3. Just for writing these structures, you get so many points. These are the easiest ones to get because all you have to do is leave one carbon untouched and you just rotate one of the carbons, flip-flopping them throughout that rotation, right? Now you have to circle the most stable one. The most stable one has the smallest amount of strain, right? Ethyl and ethyl gauche strain. Because again, when we're dealing with Newman projections and we're dealing with alkyl groups that are close to each other, we're dealing with gauche strain. Ethyl versus ethyl strain is a lot more energetic or unstable than ethyl versus methyl. It's a lot more unstable than methyl versus methyl. And this makes sense. If we have two CH3s, it's going to be a lot more favorable, a lot less energetic than CH3, CH2, and CH3, CH2. Hopefully that makes sense. Okay. So if we're looking at this, hey, look, we have, what color do we want? Let's do purple. I like purple. Alzheimer's month was in November and their color is purple. We have an ethyl and a methyl. We have an ethyl and a methyl. Oops, that's supposed to be ethyl. My bad. Ethyl and an ethyl. Here we have an ethyl and a methyl. Here we have ethyl and a methyl. Here we have an ethyl and an ethyl. And here we have an ethyl and a methyl. Last year, when I was doing this, I was getting a little annoyed. Someone asked me to re-explain it, and I sounded like Mike Tyson. You take the ethyl and the methyl. I'm super tired, super stoked. Yeah, you get the ethyl and the methyl, blah, 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 all that stuff. Well, automatically we know, hey, look, what's the point of difference? These two have two ethyl. Two ethyl. Those are very energetic. Well, this one has two ethyl methyl, less energetic. Let's color code these. This one automatically, hey, the most stable one. You have the relatively smaller alkyl chains that are close to each other. The other ones have a little bit more strain. Yeah. So you guys get that? That's a relatively big concept. Hey, these are really easy. Once you know it, right? So, hey, we are looking at a trans 1-methyl-3-propyl cyclohexane. So all you have to do is show that it's trans. You can do CH3 for that methyl here. CH2, CH2, CH3. Any one of these. If you were to flip-flop them, that would be fine. That would be fine, as long as they're trans. H. This one is up. This one is down. This one is up, CH3. This one is down, CH2, CH2, CH3. Maybe H is here, H is here. When you chair flip, you do a complete reversal, even though this was up. Now it's going to be down. Or no, not it's going to be down. It's going to still be up, but you're going to push it down to that equatorial, this corner. Push it down there. Still going to be relatively up, CH3. Still up, H. Now this is down bad. Like my arrow drawing. You guys didn't see that. Down bad. Still down. CH2, CH2, CH3. There you go. You have two chair flipped stereoisomers, chair conformation models. Which one is the most stable? Well, again, if you know you have 1,3 diaxial strain, whenever you have an axial, alkyl group, that's pretty energetic. So you want the smallest alkyl group as axial, and you want the larger alkyl groups as equatorial. So the larger they are, the more equatorial you want them. This one right here has your propyl group, the larger group, as equatorial. Here it's axial. You're going to have a lot of steric strain. For the last one, hey, look, we have 1, 2, 3, 4. All right, this one is up because it's wedged towards you. This one is down because it's facing away from you into the page. If you don't know that, oof. CH3, CH3, CH3. Again, if you were to look at this perspective down here, this would be wedged, this would be wedged, this would be dotted. Yeah. And then these would be our H's. Now, which one's anti-periplanar? I'm just joking. Igor, you have a question?
Yeah, hey Patrick. I was just wondering if you could go over again at this last question that you just circled. How or what made you know that that one is the most stable?
Yeah, the most stable because, again, we have the largest group, equatorial. It doesn't matter if this group was a methyl or an ethyl group, as long as the largest group is equatorial. That's it. Yeah, that's it. The largest group being equatorial is the more favorable one.
Got it. And
Or
you
the
said
most
something
amount of
about-
alkyl groups, equatorial. Like if you had to choose between like a cherry conformation like this, right? Let's say you had CH3, CH3, CH3. This is axial, it's equatorial, equatorial. If you were to chair flip it, this would be equatorial, this would be axial, this would be axial. Again, the same logic applies. You want the most alkyl groups or the largest alkyl groups to be equatorial. So this conformation is favorable because we have the most alkyl groups equatorial. So don't overthink it. The largest alkyl groups and the most alkyl groups we want to be equatorial. That's it. He won't make it too hard. Don't worry. But now let's apply it here. Okay. Carbon 1, we have that methyl group facing up. CH3. Carbon 2, methyl group facing up. CH3. Carbon 4, methyl group facing down. CH3. Down. And then we just have some H's here. Now let's do a chair flip. Carbon 1, still up. CH3. Carbon 2, still up. Tutorial. Oops. Hold on. Yeah. Still up. CH3. Carbon 4, still down. CH3. H. All right. Now you have this conversation. Oh, shit. This is the exact same example I just showed you up there. Which one is more stable? Well, you have 3 methyl groups. None of them are bigger than the other, but which conformation has the most amount of alkyl groups? Equatorial. Here you have axial, equatorial, axial. Here you have equatorial, equatorial, axial. Hey, if you're looking among these 3, the one with the most equatorial is the more stable one. We want to maximize the amount of carbon chains and the sized carbon chains to be equatorial. All
Do you
right.
think he'll keep the carbon numbers on the final? Like
Well,
the 1, 3, and 4 or whatever?
What about him?
Like, do you think he'll put the numbers on the, like if he gives us a blank chair confirmation, he'd still put the numbers?
He'll put the numbers there. Don't worry. All right. We finished test 1 material. I'm going to pause the recording right here. Pause the recording. There we go. Let's continue the recording. But we might continue the recording, but we're not going to stop the party. I don't know if yeah, what the heck? It's my senior year. What's the chem department going to do? Fire me? I'm going to graduate, bruh. You got that on video. Okay. Let's move on to test 2. This is my least favorite test. Same thing for a lot of you. My least favorite test because, okay, when I took OChem 1, this was my highest test because I studied like fucking crazy. I was a fucking madman. I was so antisocial. I was like I said the word a lot. I was a hermit. I had no social life. I just, ugh, it was bad. But looking back on it now, it's not terrible. Even after taking test 3, some of this stuff, not terrible. Not terrible. Like, look at this first question. All right. Classify the following carbocation. Excuse me. Classify the following carbocation. This was really easy after test 3. A carbocation, the carbon is connected to 3 different carbons. Hold on, the burp's coming out, but it's not coming out. Okay, it's not coming out. Carbocation connected to uno, dos, trace, 3 carbons. It is tertiary. Now let's look for the alkene. Classify the following alkene as mono, di, tri, or tetra. Hey, if you know anything from your thermodynamic product, hey, look at that alkene. It is connected to uno, dos, trace carbons. It's tri. Try harder, you know. All right, now let's get to a real kicker. This is probably a very big skill that you should know. All right, I'm going to put a little star next to this. Come back to this one. All right, and pay attention. So when you're looking at a Fisher projection and a Newman projection, the big thing to note, hey, look, these are always going to be wedges. These are going to be wedges. And this is going to be dashes. The best way to describe this is if when you have a Fisher structure, all of those branches are going to be eclipsed. Because if you're looking at the Newman projection down here, these are going to be wedged. These are going to be wedged. These are going to be wedged. And then this is going to be dashed. These carbons back here. Because from your perspective, if you're looking down at an eclipsed Newman projection this way, from that perspective, it's going to be a Fisher structure. All right? And whatever is eclipsed with each other, let's say A and A are on the right side, those are going to be eclipsed with each other here. B and B are also going to be eclipsed with each other. There you go. With this in mind, I'll keep this up here in case you guys want to write it down. You're welcome to. Right here. Oh no, the A branch turned really small. I mean, really average. Really average, am I right? Okay. Let's be real here. Let's go back to reality. Okay. So with this in mind, now let's just translate this Newman projection. So if I know that they're going to be eclipsed, hey, look at these CH3s. They're going to be eclipsed down here. Whatever's your top and bottom are going to be eclipsed. So if I were to eclipse these two, it would look something like this. I'm going to zoom in. It's going to look very small, but trust me, you have the recording. You're welcome to go back. I'm going to zoom in. If I were to eclipse them, it would look like this. CH3, CH3. This carbon right here, I'm just rotating it a tiny bit. The Br would now be eclipsed with Br, and the H would be eclipsed with H. This isn't the way I like to do it, so let's just rotate the entire thing around. I'm going to rotate it around. I'll use green. I'm going to rotate it around, not one specific carbon, but just the entire structure. CH3, CH3, Br, Br, H, H. I just took that bugger. I just rotated all of it. So now it matches the thing I know. Hey, look, it looks like this. My BRs are wedged. They're in the wing flaps. The H's are on those wing flaps. And now the CH3s are facing away. So, looking at this, let's erase all this mumbo jumbo. The BRs are on this wing. BR, BR. Again, they're both wedged and they're eclipsed. And the H's are also wedged and eclipsed. That's the answer. Being able to do that on the fly is a very good skill, especially, I'm bringing up the MCAT again because I have been studying on the MCAT. I remember there was a specific MCAT question where like I had some kind of configuration for 3 different stereo centers for, I think, glycerol, some kind of fatty acid. And I had to like look at the Newman projections for different things like on the fly really fast. So if you're pre-med, this skill is very important. Oh, please, 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 please. Yeah. Yeah, Sarah, go ahead, go for it.
I was wondering, does it matter like which side you put the 2 BRs or the 2 H's on? Like if you put the 2 H's on the left and the 2 BRs on the right, would that be right or wrong? Or
That's a very good question. If this group and this group, if they were different, it would matter. It would matter because the relative configuration has to be right. But thankfully for this case, they're both the same. If you wrote it on either side, flip-flop, that's fine. Because if you were to take that thing, that Fisher structure, and rotate it in the plane, that would still be right. That would still be the same. But if they were different, yeah, you can't really do that. So you have to be very careful. But this one, it's really easy. Those things are aligned. So be careful. Be careful. Keep an eye out. And this is one of the many things you're welcome to double check if you finish your test early with like 5-10 minutes left. Feel free to double check this.
Thank you.
Yeah. What is the approximate pKa of the following compound? All right. Did he knock out this pKa in the pKa table for you guys? Oh, oops. He did it last year. It was pretty funny. Well, not funny for the students. That's really mean. But it was really funny for me because I was in their shoes. And I'm a toxic person. So it was pretty funny for me. But this proton being acidic has a pKa of 15. Yeah, 15. All right. Well, you might be thinking, well, hey, if he does knock out the pKa, what do I do? Well, first off, you're screwed. Yeah, you're going to have to guess. Second off, I can give you some values that might be really good to know, right? Some values might be really good to know. Well, you know that all of the strong acids all the strong acids are a negative pKa, right? Hydrochloric acid, -7. Hydrobromic acid, -9. Hydroiodic acid, -10. Those are really, really easy ones. Well, the functional group of a protonated alcohol is the same as a H3O plus, which is going to be around -1.74. No alcohols, no amines, no protonated amines. I mean, I wrote that really weirdly, but let's make it a little more clear for you guys. Know those. Know the pKa of a double bonded carbon, triple bonded carbon, and carboxylic acid. There you go. This one's going to have a similar pKa to H2O, which is going to be around 15 to 16. Carboxylic acid has a pKa of around 5. This one I just told you it's 15. Yeah. You're welcome to look over it, but these ones they wouldn't hurt to know. You might be asking, like, Patrick, do we really have to know that? It's okay. It's compared to the stuff you guys have been learning for chapter 10 and 11, this is nothing. These are just numbers, right? All I have to say to that is, sorry. You might be also be thinking, Patrick, why aren't you writing the pKa's for the other ones? Because I don't know them. I didn't memorize them. I mean, I did memorize them, but that's out of my brain now. I don't have to anymore. Oops.
Do you know like which chapter of the textbook or anything we could look for them in?
It's the PKA table for tests 1 and 2.
Okay.
Yeah, they just tell you. No worries. All right, E or Z. This one is a topic that many of you like. All right, I'm going to pause the recording real quick. Okay. 2 bridgehead carbons. Let's cut it in half and look at one side. For the right side, let's identify, hey, look, carbon right here. Let's look at the things it's attached to. Carbon, oxygen. Which one has the largest atomic mass? Atomic number. This one. Automatically, you don't have to look at anything else. If there's something he likes to do, if later on this is like connected to like a bromine down the chain, doesn't matter. Even if there's a larger atom at the very end of the chain, the fact that this is initially connected to a carbon means that this takes priority. It doesn't even matter for the bromine because, again, which one comes first, right? Now let's look at the left side. Carbon right here. It's connected to a carbon and a carbon. Tiebreaker. Let's look at the next layer of connections. It is connected to a carbon. Those 2 carbons being the double bond. There's 2 carbon-carbon bonds and a hydrogen. For this one, we have a chlorine, carbon, and a hydrogen. Out of these bonds, the direct connectivity to chlorine means that it is very, very favorable. Excuse me. This is the preferable one. This takes priority. They are trans. But it's not asking for cis or trans. It's asking for E or Z. We know that trans is going to be E. Let me just make a little pretty box. There you go, E. Now, this one was also a tough one. True or false? This was what we called a mini synthesis. If you take step 1, H2P-C, you know you reduce a triple bond. You add 2 H's across a pi bond, and then you might be thinking, well, hey, again, this is not the answer, but this is what a lot of people thought. Step 1, you get an alkene. And then step 2, Markov-Nikov addition of HBr. That makes sense. It would be true. But the answer is no, it wouldn't. Why is that? Because H2PD-C will reduce everything, right? This will fully reduce a triple bond to just an alkane. So in actuality, by step 1, it will become just a normal pentane. Now, if this was H2 Lindlar's catalyst, or Na and ammonium at a very cold temperature, where it just reduces one of those pi bonds, then you would proceed. Because if you only reduce one of those pi bonds, then you would get the alkene, and then you would proceed. But because H2PD-C reduces everything, this would be false. Because the true product would just be this. It would just be that. All right. Give the proper IUPAC name for the following. Yay, God bless IUPAC. Am I right, guys? Okay, let's cut across. 1, 2, 3, 4, 5. Let's look at the right and leftmost carbons. Can we expand the chain? No, we can't. All right, so let's number it. We have on the left to right 1, 2, 3, 4, 5. Right to left 1, 2, 3, 4, 5. Blue, we have 2, 3. Whoops. It'd be 2, 2. 1 for the methyl, 1 for the alkene. That's why. Right here, the methyl and the alkene. It would be 3 and then 4. Right to left, it would be 1, 3, 4, 4. Oops, 1, 1. My bad. 3, 4. Yeah. So which one takes priority? Well, automatically, left to right has the lowest numbering scheme because of that first number. So we would go left to right. So we would get 3, 4, dimethyl, pent, 3, ene, 1, ine. You might be thinking, Patrick, didn't you just say that alkenes take priority over alkynes? Yes, they do if it's a tiebreaker. If you had to pick between the two, pick alkene. But in the actual IUPAC, they're at the same level. All right. If one of them, alkene or alkyne, get the lowest number, that's the one you want to go with. If they're both given, let's say if this is hypothetically, not this problem, hypothetically two, you have to pick the alkene takes priority. That numbering scheme. Like if the alkene got 2 here, but the alkyne got 2 there, if it was a tie, you would want to give the alkene the number 2. But this one, automatically, there is no tiebreaker needed. Forget about it. All right. Would you guys like a specific example? 3, 2, 1. All right, I'm gonna keep going. Now, for this type of question, we have a cyclic structure. You know you want to start at a branch of a branch. Well, I can tell you right now, the first carbon is automatically going to be here. First off, you don't have an alcohol, you don't have an amine. Your priority group is going to be an amine, not amine, an alkene. Dang, that would have been a good rhyme if I didn't mess up. Gosh darn it. It's okay. But hey, you know that because your alkenes are priority group, one of these 2 blue carbons is going to be your first carbon, because you have to give your priority group the lowest number, so you have to start off with the alkene. Now, which one's better, the light blue or the dark blue? Light blue is better because, hey, you already have a branch there. Go with that one. So if we went with this one right here, where would we go? Clockwise or counterclockwise? Remember, you have to go through the alkene. You have to cross that bridge. So it'd be 1, 2, 3, 4, 5. You don't even have to worry about the numbering counterclockwise, because automatically you have to count through the double bond, and starting at the chloroalkene, it's automatically more favorable because you get 1, 1 numbering. So let's number it. We have 3 bromo, 1 chloro, 1 chloro, 5 methyl, cyclo, pent, 1 ene. Ta-da! All right. Now we have this ugly piece of work. Oh my God, look at it. I don't even want to look at it. Count across. 1, 2, 3, 4, 5, 6. All right. Count across, you got 6 carbons. Look at the left and rightmost carbons. We can't extend the carbon chain, so this is what we got. If you were to count left to right, you would get 1, 2, 3, 4, 5, 6. Right to left, 1, 2, 3, 4, 5, 6. Thankfully, even though this molecule is an ugly piece of work, it makes naming really easy. We would go with the right to left because alcohol is our functional group. Even though alkenes are functional groups, alcohol takes the highest priority. That would get the lowest number no matter what. So this would get 3 in the pink numbering scheme. That's the one we're going to go with. So it would be 5 methyl, hexa, 1, 4. Again, the numbers being where that double bond started. 1, 4, diene, 3, all. Yeah. Now look at this. This is an even uglier piece of work. Oh my God, look how ugly it is. I don't want to do that, but I'm gonna. Carbon chain. We have 6 carbons. Hexane. We count across left and rightmost carbons. We can't extend it further. There's no weird variation. All right. Now let's take a look. We have ding, 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 alkenes and stereoisomers. So do we have to address them? First off, no, we don't. Because if we were to analyze this, hey, look at this. If we were to look at this carbon, the things it's attached to are the same. If you were to hypothetically flip-flop them, doesn't matter. Does not matter. This is not a stereocenter. Same thing with this. If you were to take this carbon, the things it's attached to, flip-flop them. Hey, if a carbon has two of the same groups, it is not a chiral center. It is achiral. It is achiral. So you don't need R or S. Okay? So if we were to count across 1, 2, 3, 4, 5, 6, let's look at the numbering. 1, 2, let's keep left to right. I've been using blue. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Which one do we want? Well, again, remember alkenes take priority. So we would go with the blue numbering. We would get 2, 4, 4, trimethyl hex 2-ene. Now, normally a bell would ring off while I'm doing it, but I have like a little mental check note or checkpoint at the end of the nomenclature. Let me go back and double check I'm not being a dumbass, and I accounted for the E and the Z and the R and the S. For this last one, I just told you these are the same for this stereocenter. These are the same for this stereocenter. I don't need E or Z or R or S. All right, here, look, we have another alkene. This alkene has H and H attached to it. It is a terminal alkene. They're the same. There's no stereocenter. Same thing with this alkene. We have a CH3 and a CH3. They're the same. No stereocenter needed. For a cyclic structure, cyclic structures are always going to be cis. We don't need that. The only time you're going to have a trans-cyclic structure is if you have like 16 or more carbons. And we're not going to deal with that until second semester. For the top one, again, we have an alkene. But look, if you look at this stereocenter, this and this are the same. No E or Z needed. Now, if you were taking this test and you thought, man, there is no E or Z, am I like tripping right now? Normally you would think that, but then you would realize, oh, it's Dr. Berg we're talking about. Of course, he would do that, where he would put no E or Z. And that's what ended up happening. There's no E or Z needed for any of these, right? I remember one of the test questions for test 1 semester 2, like he had a question, circle all the following that are aromatic. And I'm like, none of these are aromatic. Am I crazy? And then I thought, no, this is Dr. Berg we're talking about. Of course he would do something like that. And then I got the question right, because none of them were right. Right? This is OChem. They love to gaslight you, just like the TAs. God, I hate the TAs, right? Okay, let's move on. So if we were to look at the E, not the E, the R or the S, you have to denote the priority groups. For the top leftmost, we have our chiral carbon. Oxygen would obviously get 1. Hydrogen would get 4. Pretty much always the case. Hydrogen will always be the 4th one because nothing's smaller than hydrogen. We're keeping it atomically. Now we have to look at this one and this one. Which one takes priority? Well, let's look at the connectivity. H, 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 C, H, H. All right. I have a video on this specifically. Take a look at it if you don't get this. But obviously CHH takes priority. This would be 2. This would be 3. If I were to look at the structure, it would be R. Because if I were to rotate that backwards, right? If I were to flip it on its head and have the top portion facing, that tail facing away, it would go from the top to the right to the bottom. It would be R. Some of you might be like, what the heck? That's not a very good explanation. Well, R and S is very hard to describe verbally. It's best to look at it through the model set, which he does let you use on the final as well. If you were to build a model set, you could see, hey, if I assign that, that white, not the white, the green, red, blue, I think it was white. you would account and see that it is R. You're welcome to do that on the test. Same thing here. Okay. H is going to be 4. Okay. Now let's look at the connectivity. We have C, 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 H, C, C, H. Which one takes priority? It would be this one. This one takes priority. Why is that? Well, if you have a tie between the two, CCH versus CCH, go with the double bond. Go with the double bond. Patrick, why is that? I don't know what to tell you. No, it's hex. It's hex 2, not hexa. Hexadiene. But yeah, hexadiene, hex 2. Yeah, they're right. They're right. This would be 1. If I had to choose between 2, 3, 2, 3. This would be 2. This would be 3. If I were to look at that, 1, 2, 3, that would be R. Another question you might be asking, well, hey, what about the reversal rule? H is not on a dash for the first or second one. Why don't we just reverse it and just count in things normally? Well, when the H is on a wedge, definitively reverse it. But if you remember in the video, when H is on a line, it's a little bit trickier to see, and you're going to have to actually visualize it, rotate it in your mind, and actually see, because it's a little ambiguous when it's on a line. But hey, perfect segue to part 3. H is on a wedge. So I know for a fact I'm going to reverse the shit out of this. Okay? Let's take a look at the connectivity. So, first off, chiral carbon, right here. N takes priority. Even though the top carbon is connected to 2 oxygens, you're looking at direct connectivity. N is bigger than carbon on the top and the bottom. So, N takes priority. H is number 4. Now let's identify top or bottom. Which one's number 2? It's going to be the top one. 2 oxygens, 3 carbon-oxygen bonds, while the bottom one has only 1 carbon-oxygen bond. So this is number 3. If you're to look at it, 1, 2, 3. This would be S. But because H is on a wedge, you're going to have to reverse it. It would be R. Arg. Okay. This one, take a look again. Let's do the top one first. For the top one, this is 1, direct connectivity. This is 4, direct connectivity. Now, for here, you have a carbon and a carbon. Which one takes priority? This carbon is connected to a bromine. This one is connected to 3 H's. Automatically, this bottom one's going to be the real money maker. This one's going to be 3. Nope, 2. This one's going to be 3. If we were to look at that, that would be 1, 2, 3. That would be S. But because the H is on a wedge, it would actually be R. Arg. Here. Erase this. Move this right up here so I have more room to do this one. Chiral carbon. Okay. Bromine obviously takes the first priority, largest atom. Hydrogen takes the 4th priority. Now let's look at the direct connectivity. Carbon here, carbon here. This carbon is connected to oxygen. This carbon is connected to carbon, hydrogen, hydrogen. This carbon takes priority. Oops, I did this thing again. 2, 3. If I were to rotate it and do the counting, well, let me not rotate. That's how I do it in my head. If I were to do the counting, 1 to 2 to S, that would be, normally you would think R, but because the H is on a wedge, it would actually be S. That is the actual thing, the reversal. Because again, your 4th priority is definitively on an S. Can you explain why the second one's not S? Because of the numbering. If you were to rotate it around, let's like just rotate it this way, it would be R. You'd be going clockwise. This way to this way to this way. Right? The alkene takes priority over the propyl group. The isopropyl group. The propan-2-il group. Chiral versus achiral. They just hate you, don't they? Okay. Chiral versus achiral. Let's draw it out. Is this symmetrical? If I were to do a line of symmetry right here, no. Or if I were to do a line of symmetry on that plane, vertical, no. That would be chiral. What about for this one? There you go. There is a line of symmetry right here. Even though those chlorines lie on the plane of symmetry, those chlorines are being cut in half by that plane of symmetry. This would be achiral. For this one, is it chiral or achiral? When you're looking at a Newman projection, just eclipse it. If you were to eclipse it, let's eclipse this with this, you would get something that looks like this. CH3, CH3, H, nope. Yeah, the front was H. OH, OH, H. These are not symmetrical. There is no plane of symmetry because if you were to draw the Newman projection, it would be CH3, CH3, H, OH, OH, H. Hopefully you're learning that from the previous page. Hey, look, not symmetrical. This is chiral. There is no plane of symmetry anywhere. Now let's look at this one. For Fisher projections, it's really easy. You either have a plane of symmetry here or a plane of symmetry here. If you were to look down here, it's not symmetrical. Nope. But if you were to look right here, it is symmetrical. Look, O and O, symmetrical. Methanol, methanol group, symmetrical. This would be achiral. Now let's look at this one. Is this chiral or achiral? This would be chiral. There is no plane of symmetry here. There is no plane of symmetry here. Now you might be thinking, what about that weird thing with a point of symmetry? Because there's something in your head that might think, all right, you have a cyclic structure. You have dashed and wedged halogens. From a lot of the tests you've seen, he's made them point of symmetries. Point of symmetry just means the plane of symmetry is in the middle of the cyclic structure. If you were to build the model set, they would be superimposable, right? No direct plane of symmetry, but they would be meso compounds, so they would be superimposable. But for this one, this is not the case, because if you were to build it, they would not superimpose on each other. If you were to build the model set, they would not superimpose. And you have an odd numbered cyclic ring. If the other bromine was also dashed, would it be achiral? Yes. If this, perchance, was dashed, it would be achiral. The plane of symmetry would be right down there. That would be right. Yeah, that would be achiral. But life is hard. Berg hates you. Bootcamp hates you. I don't hate you. This is chiral. So let's make it real pretty. Boom, boom. How mad would you guys be if I did that? Anyone cringing right now? Oh, that's not fitting it. I'm so mad. Yeah. Now we get to some real doozies. Okay, hey, look. You have on the top left just some of these. Now you might be thinking, hey, can I just draw a line here, flip flop it, pancake flip it, and it would be achiral? No, it wouldn't. This ethyl group would be in different positions. When you're looking at alkenes, when you have E and Z, those are diastereomers. Yeah, fun fact. For this one, here and here, this is cis. Here and here, this is trans. Cis versus trans alkenes, this would be diastereomers. I'd be thinking, hey, wouldn't diastereomers need a difference in at least one stereocenter? Would be right. Your two stereocenters are going to be right here. These stereocenters are the same, but this one and this one, they're different. They're flip-flopped. Yeah. Now let's look at this one. What kind of isomers are they? Well, I know, hey, let's look at the chemical formula, right? The chemical formula, there's one Cl, one Br, and one F cyclohexane. If you counted out all the atoms, they're the same. But now let's look at the isomerism, right? Well, I think a cool thing to note, chlorine is geminal to fluorine here. Chlorine is geminal to bromine here. Uh-oh. Different connectivity, constitutional isomers. What's going on with my nose right now? It's okay. We're here.
Hey, Patrick,
What's up?
do you know if on the final Dr. Berg, if you'll give us the definitions for each of those?
Yeah, I'll give you the definitions. Yeah.
Yeah?
Yeah.
Awesome.
Yeah, he'll give it to you the definitions. All right. 1, 2, 3, 4. Should be up, down, down, up. This would be up, mm, 1, 2, 3. Oh, hold on, I drew that wrong. I think I drew that wrong. Oh, wait, no, I drew that right. Yeah, that's right. 1, 2, 3, 4. 1, 2, 3, 4. If I were to pancake flip this up, it would be down CH3, up CH3, down CH3. Let me color code it so you guys can put together what's what. This one pancake flips down to this. This one pancake flips up to this. And this pancake flips up to this. Color coding it, or just to flip it up, I can tell that this entire structure is an enantiomer of this one. If I were to put them over each other, planar, they would look like mirror images. Enantiomer.
How do you know where to start counting on them?
It's arbitrary because the connectivity will still be the same. Yeah.
Okay, and you have to count in the same direction on both of them?
I just did, just to be sure, try it out. I don't know if that actually helps or not, but like for here, I did 1, 2, 3, 4 going this way. This one I did 1, 2, 3, 4, again going this way. But as you can see, the one that's proximal to the CH3 is 4 here, but this one that's proximal to CH3 is 1 here. Again, it's arbitrary because the connectivity should still be the same. So as long as the structure is right, you can still manipulate it. So I don't think
I had counted it like so that the one pointing straight up, like you can clearly see is up, was 1 on both of them, and that I thought they were the same.
not. Yeah. I don't
So,
know.
like-
I don't know how to describe it.
Okay.
Yeah. Some people just straight up did this. They're like, oh, that's an enantiomer. They did. Props to them. But if you, for chair conformations, it's a lot harder to figure it out if you keep them as chair conformations. The easiest way is to make them as planar cyclohexanes and then compare it. And when you do make them planar cyclohexanes, the numbers should be arbitrary. I think you should be pretty good on that. So if you do it the way I did it, you should be pretty set. Hopefully that helps. Yeah. For whatever you did, I don't know what you did. or if that's the ideal way, but this is the way I would do it. Keeps things relatively simple because these planar high cycle hexagons are relatively easy to compare. All right. Let's take a look. If I were to pancake flip this down, this would go down here. Pancake flip. This would flip down there. Here, just erase that. Up CH3. This would pancake flip down here. CH3. See, I just pancake flipped it over. And what do you know? This is the same as that. These are the same. Ooh, here's a doozy. What are these? Same diastereomer and enantiomer constitutional isomers. Well, if you look at the chemical structure, these have the same chemical structure and the same connectivity. So you know that these are stereoisomers. Now, let's look beyond that. This one has the bromines on the left side. This one has the bromines on the right side. You might be thinking, well, hey, can't you just pancake flip it over? Never pancake flip Fisher projections. But what if I kept it in the plane and I rotated it over, then it would paste over. But the thing is, that would be true, like we talked about before, if the top and bottom were the same, but they're not. If you were to pancake flip this over completely 180 degrees, CH2, CH3 would be on top, but even if the BRs would align with each other, it would be out of whack. So these are enantiomers. Mirror images of each other.
So
Yeah.
if the top and bottom were both CH3s and you flipped it, would they be the same?
Yeah. Now flip, rotate again.
Or rotate, yeah.
Yeah. I know what you mean, but you'd be right. If they were both the same, if you were to rotate it, yeah. Because Fisher projections, you can always rotate, but never flip. If you were to rotate it and it's superimposable, they're the same. But for this specific case, if we were to rotate it, the BRs would be superimposable, but that CH2, CH3 would be imposing on the CH3, which is not the same. Hey, look at this. We have another Newman projection versus Fisher structure. How do we do this? Well, we just rotate it. Let's rotate the back carbon. Now you might be thinking, why am I rotating that back carbon? Well, if you remember, CH3s are facing away from you. If you remember the template structure I drew up above, this is the easiest way to do it. If I were to have this Newman projection eclipsed, CH3, CH3, if I kept this front one the same, OH, H, this back one, CH3, CH3, BR would be over here, H would be over here. I just rotate that back carbon. Look, OH is eclipsed with H, BR is eclipsed with H. Same here, it is 3O. They're the same. Not only that, but the pieces that are facing away from you from that little perspective point are the same. These are the same. So the eclipsed structures are aligning with each other. They are correct, and everything else is correct. These are the same. Whoa. Something we all love, mechanism. Now this one's really easy. All right, let's first break the carbon. So we are given this structure, and we're given the following reaction. We get two products, 1 chlorobutane, 2 chlorobutane. Let's draw the intermediate for the mechanism of 1 chlorobutane, and then the mechanism that creates 1 chlorobutane, the intermediate, and the mechanism that creates 2 chlorobutane. Right. So the first step is the rate determining step, creating the carbocation. You have the electrophile, hydrogen, being attacked by the nucleophile, the double bond. Right here. Rate determining step. C, C, H, H, H. All right. For 1-chlorobutane, the chloride is going to be your nucleophile and attaches wherever that carbocation is. So for creating 1-chlorobutane, the carbocation would be here, and the H would be here from that hydrochloric acid. So for the next step, this would attack here. The nucleophile goes to the carbocation. Electrons go from where there is to they ain't, to where they ain't. CH3, CH2, C, C, H, H. Let me do that. H, H. There you go, 1-chlorobutane. And again, just to reemphasize, the formation of your carbocation is always going to be your rate determining step. Rate determining step. There you go. Right. Same deal. Carbocation forms here, H, because we're trying to form 2-chlorobutane. CH3. That's why it's so thin. I never changed it back. ClH. There you go. Which product is formed? Product 2-chlorobutane is formed because more stable carbocation. Secondary carbocation versus primary. Secondary is formed. What dictates the product is formed? Stability of the intermediate. There you go. Because again, your carbocation is the intermediate. Ooh, another fun one. All right. Reactions. All right, you react this alkene with HCl. You know, hey, look, we're adding across the alkene. There's going to be carbocation intermediate, shift possible, Markovnikov, neither anti nor syn addition because you have a carbocation intermediate. Your nucleophile can add to either face, top or bottom. So our product would be this. Let me make it a little more consistent. ClH. You can write that as CH3. You're welcome to, but I'm just trying to show the viewers where the HCl is adding to, right? The Cl is adding to the tertiary carbocation because it's Markovnikov. Shift possible. It's already tertiary. There's no need to improve it. It's your product.
Patrick, we had a quick question.
Yeah.
Regarding the mechanisms on the last page or the previous page.
Oh, yeah.
Is it the same 3 that we need to know from test 2, or are there going to be additional ones that we should know as well?
So are you talking about are you talking about for the final?
Yeah.
Yep.
Unfortunately, you guys are not gonna like this. It's gonna be fair game. Here, let me give you the ones that is possibly are. So regarding your test 2, your big 3. Your big 3. For test 3, thermodynamic versus kinetic product. For your new material, this is what's most likely going to be the mechanism. Most likely, there's a good chance it can still be thermodynamic versus kinetic product. Most likely going to be new material for the elimination via H2SO4, elimination versus PCl3, PBr3, elimination versus POCl3. Actually, this one's not as likely. I don't think I've ever seen that one before. Cross that one off. No, not that one. The only organometallic I would take the time to would be your Grignard. Your Grignard mainly because it follows a similar mechanism where you use a carb anion to some way just open up a carbon oxygen double bond or epoxide and then you stabilize it with an acid. HOR, some kind of ether related compound. You're making ether, some kind of alcohol, H plus catalyst, and then some kind of NaOR, HOR. These four you can pretty much see in the problem set. Yeah. These are in the problem set. The mechanism you don't have to show in the problem set, but for the new material, these are the 5 that I would know. Not everything, thankfully. You don't have to know Suzuki coupling, nor the Coop rate. Thank God, because I don't even know it. I don't need to know it. But yeah. You might be thinking again, Grignard, why do we need to know that? Well, first off, you learned it, but even if you said second semester we might learn it later, you do. Why can't I just learn it then? Well, if you learn it now, you'll be better off for semester 2. And if it shows up on the final, you won't be as screwed. Basically as is. Out of all of the organometallics, Grignard's probably the most simple one because organocuprate, yeah. That's a PB3, PBR. That's supposed to be PBR. My bad. There you go. Yeah. Okay. Let's move on. Thank you for catching that. Okay. H2O, H2SO4. Again, we have a carbocation intermediate. Shift is possible. We have a Markovnikov addition. And there's no syn, no anti-addition because it can add to either phase of the carbocation. So the carbocation would initially form here. Right? Now, you might be thinking, hey, there's a possible tertiary spot right there. Can it shift? No, it can't. It can't shift over one carbon. More than one carbon. It's too far away. It can't shift. So it's just going to add OH here, add H here. H2, CH, CH2, CH3, OH. Again, for that rightmost carbon, you're welcome to write it as a methyl group, but I just wrote it this way to show what's being added. All right, let's go down. 1 equivalent of HBr, 1 equivalent of HCl. For your first product, you would get CH3, C, CH3, Br, H. Can we use the loop for these in theory? You could. Yeah, it's better off to just know the actual material. I don't see the loop being that useful because you might know it as a map in your head, but you have to know the actual concept to accomplish the test. But if you're already like memorizing loop, go for it. It might work for you what didn't work for other people. Step 2, CH3. Could the BR go on either one? Yeah, you'll see later on it's going to be symmetrical. Let me finish. CH3, BR, H. This is the thing you have to know. When you add the Cl and the H, these are going to be geminal on the same carbon. Yeah. You could do it on the right carbon, flip-flop it. Either one works. It's going to be symmetrical. Do we get the blank loop on the exam? I don't know. Exam structure is more Dr. Berg's way. All right. H2B down C. Now, the thing to note, even though it reduces everything, the triple bond and all that stuff, it is still syn addition. All right, syn addition. This is how I would write it. Syn addition. So carbon, carbon. I would make sure the methyl groups are still trans to each other. And the deuteriums are also still trans to each other. Oops. You can do it this way, but it is encouraged that you draw it as a Fisher structure. Because even though I drew it like this, I would obviously say, hey, this is still going to be 3O. Even though you have syn addition, they're trans, they're going to stay T. T, trans, syn addition, 3O. You're going to keep that trans-like behavior. 3O. But another way you can draw this, let me make a very bad Fisher structure. DH, HD, CH3, CH3. Personally, if I was going fast, I would draw it like this, but we encourage you to draw it as a Fisher structure. So if you're doing this on the test, the reaction page is usually going to be at the very end. So I would draw it whatever's comfortable for you. And if you have time, double check, make sure it's in a Fisher structure if needed. Yeah.
If they're gonna count us wrong for not having a Fisher structure, will it say that? Because like I know on test 2 I got one wrong because I didn't
Ask
put in
ask
Fisher
him on
structure.
Wednesday.
Okay.
Say honestly. Yeah. 03. Wow. This one's really easy. You take a pair of scissors, you cut down here, and you make aldehydes. Or some kind of carbonyl. It's from that left side. There you go. That's it. Take scissors, chop that alkene, put oxygens there. That's all you need. All right. H2O, H2SO4, HgSO4. You know you make ketones. That's all you make. If it's internal, you make ketones on either one of those carbons. If it's terminal, it would prefer to make a ketone on the internal most carbon right here. That's just being added. Don't worry, that H from before is still there. So in actuality, it would be H. I'm just showing the blue to show what's added. MCPBA. MCPBA is just making an epoxide. You just got to show that it's syn addition. Syn addition retains the stereochemistry. If you just drew the lines, that is incorrect. You need to show some kind of stereochemistry. This is accepted. Or a Hayworth structure is accepted. CH3, C2, CH2, CH3, HCH3. Either one of those ways is accepted. You just have to show at least one way or another that you know the stereochemistry. You know what's going on. You know what's going on. All right. This is going to be hydrogenation. This is going to be trans. Not tan, tran. You know that the double bond you make is going to be trans because this is solvating it with sodium, or you can use lithium with ammonia in a very cold temperature. All right. If you do this, you will only reduce one of those double bonds or one of those pi bonds to make a double bond. I don't know. You just do CH3, CH2, C, 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 H. There you go. This is being added. Okay, last one. BH3, THF, NaOH. When you're dealing with an alkyne, if it's terminal, it would want to add an O, double bonded O to the terminal most carbon and make an aldehyde. But if it's a double bond, you're just going to do anti-Markovnikov addition of OH. Syn addition. Right? Now, do you have to show stereochemistry? Yes. For this case, you might get away with it because CH2 is achiral, but the fact is, just be safe. Don't half-ass it on the final. This is an OChem final, you know? Yeah. With that being said, we're now to test 3 material. We're going to take another break. Pause it. I restarted the recording, but I want to make sure you guys know if word gets out that I was doing this, this never happened. This never happened. Yeah. What kind of TA would drink water while they're doing a review session? None, because that's unethical. What? Yeah. No, forget about it. I would never do that. I'm drinking water here. Granted, it might look like It might look like a peach Moscato. Yeah. All right, let's just move on. Test 3, the final test. Thank God, right? Circle the proton HA or HB, which of the following is exo? If you remember that little diagram I drew in the review session, let me redraw that. Anything facing away is exo. Anything facing down or towards the double bond is endo. Oh shit, I'm writing exo. Boop, 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 boop. Endo. There you go. You got to memorize that. What's exo and what's exo? If it's facing away from the double bond, it's exo. If it's facing towards the double bond, it's endo. Easy as that. Which of the following is exo? If you had memorized this, like I showed you in the review session, this would have been an easy point. Circle all the following that are aprotic. If none are aprotic, don't circle any. Well, the protic atoms are always going to be on an oxygen or a nitrogen, right? So circle all the following that are aprotic. Well, hey, look, you have hydrogen on an oxygen. That's protic. That's a carboxylic acid. That's vinegar. That's acetic acid. Here you have oxygen. It's an ether, no hydrogen attached. Here you have ethanol. Holy shit, it's ethanol. You have a hydrogen attached to an oxygen. And then to the rightmost side, you have a hydrogen attached to a nitrogen. All of these are protic. But this ether is aprotic. There are no hydrogens on the oxygen or nitrogen. Okay, next one. Circle the best nucleophile in methanol. Methanol, would you look at that, is a protic solvent. If methanol is protic, if you have a protic solvent, the best nucleophile is going to be the largest one. Straight up. If your solvent, right, aprotic, it would be the strongest base. It would be the nucleophile, or the base that is the most nucleophilic. So if hypothetically, what I'm about to write in pink is a hypothetical. If this was acetone, the best nucleophile would be OH. It's the strongest base. Okay? Circle the most stable ion. This one is primary. This one is tertiary. This one is secondary, allylic. So it's somewhere between secondary, and if it were to door hinge over, it would be tertiary. So if it's somewhere between secondary and tertiary, allylic is my best bet. Is that one. Circle the most stable carb anion. This, I'm going to put a very special star. This is a general knowledge question that has a very good chance of showing up in your final, because what he talked about is carb anion stability is the complete opposite of carbocation stability. The less substituted carb anion is the more stable. So we have primary, secondary, tertiary. Primary is more stable. If these were carbocations, tertiary would be more stable. But for carb anions, the less substituted, the more stable it is. Now, this question is a very hard question. Why is 2 allylic greater than 3? Well, because your allylic structure, you have to look at the carbocations. If your tertiary structure is just straight up tertiary, but your allylic structure is secondary and tertiary, well, hey, it's a lot more stable. Because on top of being tertiary, it's also secondary. So that's why. For the people watching the recording, there was a Zoom chat question on why is secondary allylic greater than tertiary allylic. It is because of this specific problem, because the secondary allylic has a cofactor of being tertiary as well. Okay, now to revisit this question, it is very hard, okay? But the thing is, if you know how to door hinge very easily, this is very easy. Let me paint the picture. So the first rule you have to know, if you're writing this in person, really pay attention for this one because this is a very likely question. Again, on the test, start on this one. If you're watching this in a recording, you're welcome to replay it. The first rule, when you're dealing with conjugated alkenes, and they're conjugated, the inner carbons are the ones where the carbocation initially starts. Because again, if you start the carbocation here, then it can door hinge over to the next ones. So if you know, okay, the inner alkene carbons are where the carbocation starts, it's going to start here. It's going to start here. But between B and C, it's also going to start here and here. These 4 spots are where the carbocations will initially form. Okay? Not here and not here, because then they would be isolated. So I'm going to color code it. If you are looking at bond A, here, let me do this. If you were to break bond A, the carbocation would initially form here. If you door hinged it over, carbocation would form here. Door hinge it over, carbocation would form here. If you are struggling with this topic, revisit resonance structures. Because again, first off, carbocations, when you're dealing with conjugated alkenes, form on the inner carbons only. And when you're dealing with resonance structures, you have a door hinge maneuver that can move around that carbocation. So this is going to be A. Now let's look at B. For B, if you were to break that carbocation and form here, you would have a carbocation. Let's bring it over here. Now, look at this. You can't door hinge it over there. It would be isolated. Isolated alkenes and carbocation systems, not favorable. We don't really like that. So what if we were to initially draw it here? Let me keep that there. Not possible. Alkene B over here. Let's door hinge it over. Alkene B would also have a carbocation here. This would be B. Now let's take a look at C. If we were to break bond C, we would see that, see, the carbocation will form again here on the innermost carbons, right? Let's make this a pretty lime color. Door hinge maneuver, secondary. Door hinge maneuver, secondary, or primary. Now we look at all the possible carbocations. First off, what I can tell you right now, B is not the most reactive alkene, because no matter which way you break it, it's going to create an isolated alkene. Right here, this cannot attack over there, not attack, door hinge over there. This double bond cannot go over there. They're going to be isolated. That is not favorable. Either way you break it, your carbocation will only be shared among 3 atoms. While for A and C, your carbocations will be formed among 6 atoms. So now let's compare A and C. A and C, you will have a secondary, tertiary. For B, you'll have a primary, secondary. If you're to look at all 3 of these scenarios, A would be the most reactive. Now you might be thinking, Patrick, how the hell am I supposed to know this? Sucks. Because the thing is, the thing he wants you to know is, where will the carbocation initially break? Where will the alkene initially break? Where will the carbocation form? The innermost carbons. Well, once you start out at those innermost carbons, which one gives me the most stable sets of carbocations? Because if you know back, if you watch the thermodynamic versus kinetic product video, the most reactive alkene gives you the most stable carbocations. And the same logic here. The most reactive alkene gives you the most stable carbocations. So let's see which carbocations are the most stable. For A, you get secondary, secondary, tertiary. C, primary, secondary, secondary. And for B, you get primary, secondary, or primary, tertiary, but they're isolated. Not good. So this is what you would get. All right. A little bit of a tough stretch, but honestly, you have a lot of, I don't know how to describe it, buffer in your final. If this doesn't make sense to you, focus on the other stuff, because I'd rather you guys get like a 90. Hear me out. A 90, rather than like focus or fixate on this type of question and get like a very bad score because you didn't study anything else. If this doesn't make sense to you, come back to it. Come back to it. I know I spent a lot on that, but let's just move forward. Okay. Circle the proton that's best eliminated by E2. Well, first off, your bromine is here. What hydrogens can pop off? Beta hydrogens. This is an alpha hydrogen. This is a beta. This is a beta. So you have these two possible beta hydrogens. Oops. If you were to draw both scenarios where you had both beta hydrogens, B, across from the bromine, you would be able to see which one is more favorable. CH3H. There we go. So for the beta 1, all right, let's do beta 1. Beta hydrogen 1, hydrogen 1, CH3 would be over here. Beta hydrogen 2 be over here. Let's do beta hydrogen 2. CH3 would be over here. Beta hydrogen 1 would be over here. Which one is more favorable? Well, for this one, you have gauche strain. For this one, you have no gauche strain.
Yeah. What are Gabby and Madison graduating?
So you have this beta hydrogen being more likely to pop off because there's least gauche strain. This configuration is most likely to exist. This is the most probable hydrogen to be popped off. Yeah. Now let's look at this. Okay, if I were to look at the following, which of the following bromoalkanes can do E2 elimination to form alkene 1? Well, alkene 1 shows cis phenyl groups, all right? Cis pH groups. And we know that whatever Newman projection you have, your bromine has to leave with an anti-periplanar hydrogen. So if we were to redraw these, let me do this to make it easier. PHCH3. You guys ready to watch some magic? Boom, 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 boom. Look at that. Look at that. The first one, if we were to make this carbon up top, H, PH would be here, CH3 would be here. If we were to make this one up top, it would be H, PH, CH3. This one up top, H, PH, CH3. Oops. I wrote that wrong. Oops. I didn't even realize that. My bad, you guys. and try to pull a doozy on me. PHCH3, PHCH3, PHCH3. Okay, as we were. This one up top, HCH3, PH. Now, if we were to eliminate the bromine and the subsequent hydrogen, let's look at which phenyl groups are cis. These phenyl groups are cis, and these phenyl groups are cis. Well, this phenyl group and this phenyl group, they're trans. This phenyl group and this phenyl group, they're trans. So we know when we align the bromine and the beta hydrogen, these two giving us cis indicate that these two are our preferred bromoalkanes because they produce the same cis phenyl groups. Uh-oh. Oof, SN2E2. Let's power through this, you guys. Secondary, tertiary, primary, secondary, benzylic. All right. All right, let's move forward. Okay. We have a base or nucleophile equals our solvent. We have a cold temperature, so it prefers SN1. We have a weak base. We have a small strong base. We have a large strong base. We have a base equals solvent prefers E1. Now let's work through it. Okay, first what I'm going to do is going to be the weak base because the weak bases are going to be easy. They either do SN2 or they don't. All right, let's take a look. Secondary, SN2. We know this. Check this out. Tertiary, no reaction. One thing that it doesn't react with is tertiary. Primary, SN2 works out. Secondary benzylic, as long as it's not tertiary, it'll do SN2. Next one, let's do the top row. Okay, base equals solvent, prefer SN1. Secondary, no reaction. Tertiary, there is a reaction, it's going to be SN1. Primary, no reaction. Because again, secondary, primary, there's no reaction for SN1. Secondary, normally it would be it would be no reaction, but because that carbocation is stabilized by the benzyl group, you would have SN1. Yeah. Let's do the bottom row. All right. Now you have a solvent equals nucleophile, prefer E1. E1 is always going to be Zaitsev. Secondary, no reaction. Tertiary, there is going to be E1. Primary, no reaction. Secondary benzyl, it would be E1, and there is a beta hydrogen to go towards. It is E1. Now let's get towards the tougher ones. Let's do purple again. Small, strong base. Okay. Secondary, E2 Zaitsev. Tertiary, E2. It would be Zaitsev, but this is the real kicker. Not tertiary. Methyl group, methyl group, methyl group. This tertiary, even though it's tertiary, all three beta hydrogens are identical. There is no regioselectivity. One beta carbon is no different than the other beta carbons. There is no Zaitsev-Rothman. Which one's more substitute? Let me ask you that. Neither of them. They're all the same. Which one's the least substituted? Neither of them. There is no Zaitsev. There is no Hoffman. Let's go back. All right. For primary, small strong base, we'll do SN2. Secondary benzyl, it'll do E2. It'll be E2 Zaitsev. But here's the real kicker again. There's only one direction to go. If there is no regioselectivity between your beta carbons, there is no Zaitsev or Hoffman. No regioselectivity, no Zaitsev, no Hoffman. There's only one direction to go. It's only E2. Large strong base. Let's run it back. Secondary, E2 Hoffman. The Zaitsev would go this way. Hoffman would go this way. Tertiary, E2, not Hoffman. Because, again, no regioselectivity, no Zaitsev or Hoffman. Primary, this would do E2. And again, there's only one way to go for this one. also E2, there's only one way to go. Even though that these right here would normally be, not these two would normally be Zaitsev and Hoffman, there's only one way to go here, and there's no regional selectivity. Ah, I messed that up. No regional selectivity. Those
Why
are,
did they go towards the benzene ring?
how many hydrogens are on this benzene? There's no hydrogens on this. There's no hydrogens.
Oh, okay.
Yeah. Yeah. Okay, let's move on. Resonance structures. How do we draw resonance structures? Well, this is going to be really easy. Why? Door hinge maneuver. What? That's crazy. Door hinge maneuver. If you don't know what door hinge maneuver was, I'm sorry. All right. Now let's do another door hinge maneuver. Pop. We go like this, like this. All right. Now let's circle the most stable. Well, first off, which one has the most amount of bonds? They both have 2 pi bonds. Which one has the least amount of formal charges? They all have the same amount of formal charges. Now let's look at the location of the formal charges. Primary, secondary, secondary. These two are more stable. Now let's take a look. More formal charges. Let's draw resonance structures. Now, what you can do, door hinge maneuver. Boom, like this. Or you might be thinking, well, hey, if I were to build a resonance structure from here, door hinge back, it would do the same thing. But something that you should know, that you can also build a resonance structure from the beginning. You can go either direction. We're just building resonance structures. If I were to instead draw a resonance structure right there, or a double bond right there, excuse me, well, you would get something like this. That. Now, which one is more stable? Here, let's make this purple just to keep that color-coded consistency. Which one is more stable? Which of the following has the most amount of bonds? This one. I don't have to look at anything else. The fact that it has the most amount of bonds, automatically most stable, bada bing, bada boom, I'm done. Now let's look over something that I covered very in depth in the video. So I'm going to glaze through this, because if you want me to elaborate, watch the video. Show the stepwise mechanism for the production of product 1 and 2. Make sure to show all intermediates, formal charges, and resonance structures. Well, for product 1 and 2, I can tell we're breaking alkene A, because that initial alkene forms here, and the resonance structure puts that alkene right there, which aligns with product 1 and 2. So let's, I don't know why I drew that. HBr, shabang, shaboom, rate determining step. We would get boom, boom, boom. Carbocation forms here, plus Br minus resonance structure. Hey, what if we had that double bond form over there? Yeah. Positive charge here. Resonance structure, bada bing, bada boom. Now let's add the nucleophile. Let's keep it black. Br. Okay. There's a rate determining step. The first step, this is going to be a tertiary carbocation, primary carbocation, just personal notes. This is going to be my 1-2 addition. This is going to be my 1-4 addition. Okay. Just because, again, the 1-2 addition, no resonance. 1-4 addition, there is resonance. Okay. Now let's look at the next one. Alkene B. Show formation product 3 and 4. 3 and 4 are going to be right here. I know that because we break alkene B, carbocation forms there. And we show resonance structures is going to form here as well. And that aligns with product 3 and 4. So were we expected to write what the rate determining step was? No. I'm looking at the rubric right now. It was not a point. Don't worry about the rate determining step. I'm just re-emphasizing the fact that the formation of the carbocation is always the rate determining step. That's all it is. Repeat after me. Formation of the carbocation is the rate determining step. And that applies to semester 2 as well. All right. So as you move along with your OChem career, rate determining step, if you're in a bind, formation of the carbocation, easy peasy lemon squeezy. All right. Now let's break HBr. Boom, 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 boom. Shebang, shabang. Whoops. I like that to be in black, keeping consistent. Boom, boom. Carbocation. All right. Resonance structure. Oops. Here we go. Door hinge maneuver. This would form there. All right. And then we would have that Br, that bromide. Let's show that. Attack. We would get boom, boom. This would be our 1-2 addition. This would be our 1-4 addition. This would be secondary. This would be primary. Just some personal notes. Now let's identify it. Which of the following is your thermodynamic and your kinetic product? Low temperature is your kinetic product. High temperature is your thermodynamic product. Now, if you're trying to decide, well, which one do I choose? Well, you always have 4 products, 3 or 4 products. The most reactive alkene will give you your thermodynamic and kinetic product. How do you determine the most reactive alkene? Look at the carbocations. This one gives you tertiary and primary. This one gives you secondary and primary. So automatically, hey, this is the best set of carbocations. I know that alkene A is more reactive. I don't have to look at product 3 and 4, which is derived from alkene B. Product A is all I have to look at. So let's just look at product 1 and 2. Product number 1, 1-2 addition, kinetic product. Your 1-2 addition is always your kinetic product. Your thermodynamic product is always the most substituted alkene. Let's look at the substitution pattern. This alkene is mono. This alkene is tri-substituted. So this is your thermodynamic product. So product 1, product 2. That's it. Again, if you have problems with that, rewatch the video. I made an entire video on that. Excuse me. Now let's look at this. Woo! What a doozy. 1,2 dibromobutane versus butane 1-all. What? Okay. So let's look at this retrosynthetic. I know that if I'm trying to get a terminal alcohol, what I can do is take an alkene, right? Take an alkene and react it with BH3THF, that reagent. Well, how do I get from dibromo to the alkene? If I just did one elimination, there would still be the bromo there. Not the easiest thing. Let's look at the retrosynthetic area as well. Well, if I had, let's say, a monobromo, I can do a Hoffman elimination. But from the dibromo to the monobromo, that's not the easiest thing to do, right? I can't just get rid of a bromine, at least not yet. Well, what can I do? Well, if I'm trying to do a double bond, if I can't do a Hoffman elimination, what if I did it with a triple bond? Triple bond wise, I could do H2 Lin-Lars, or you could do Na ammonium and very cold temperature, the trans addition. Doesn't matter because you're going to eliminate it anyway with this. Well, how can I get from the dibromo to this? That's a lot easier. You can do 2Na, NH2, NH3, very cold temperature as well. You can use your freakishly, that's supposed to be a C. Oops. You can use your freakishly small strong base to do that, right? So if I were to do that, well, hey, look, okay, let's take our dibromobutane. Let's react it. Let's move it over. Okay. NaNH2, NH3, negative 78 degrees Celsius. We would get the triple bond. H2 Lin-Lars catalyst, or you can do the sodium ammonia elimination. That's fine. If you use H2PDNC, again, as we saw before in one of the general knowledge questions up there, it will reduce everything. So that's not a viable answer. We'd only reduce one of those double bonds. And then we would get to the final product, the anti-Markov competition of OH with BH3, THF, H2O, NaOH, H2O2. Yeah. Oh, shit. We got one last page. Look at that. Okay. Well, let's take a look. Give me 1 second. Okay. So when your alkenes are conjugated, you have to look at thermodynamic and kinetic product, right? The most likely alkene will result from either your cold or hot temperature and what the most reactive alkene is. But when they're isolated, you straight up look for which one has the most substituted carbocation. Let's write it down. Isolated, straight up, most substituted carbocation. Straight up, most substituted out carbocation. That's going to be right here. So we know, hey, look, this is going to be our major product. That's it. When they're isolated, most stable carbocation, you know? All right, now let's take a look at this. We have would you look at this? We have a small, strong base. And we have a secondary. You might be inclined, hey, small, strong base secondary, that might be Zaitsev elimination. You might want to go this way. That would be wrong. Even though it pushes for Zaitsev, again, there are limitations for Zaitsev and Hoffman. You have to look for anti-periplanar hydrogens. Anti-periplanar hydrogens, well, if this is on a wedge, you need a dashed hydrogen. This is the only hydrogen that fits the bill. Not this one, not this one. Those are not anti-periplanar. This is the only direction you can go. So your only answer can only be this. Okay? Let's take a look at this. We got a weak base. And we have a secondary leaving group. It's going to be SN2. If it's SN2, well, see, let me leave everything in check. I don't know why I made that blue. Let's make that. Let's make it go back to black. Bromine is going to leave. H is going to come up front. The CN is going to add from the back side. It's going to be this. Right? Here we have a weak base, and we have a neither primary nor secondary nor tertiary. Why is that? Because primary, secondary, tertiary only apply to sp3 hybridized carbons. If this carbon is sp2 hybridized, it is not tertiary, primary, secondary. There is going to be no reaction. You can't do that. The only way you can react to this bromine is if with that freakishly small strong base. Because remember, the freakishly small strong base can eliminate a double bond because it can make a triple bond. But for this one, it can't. Right? Cannot. Now let's take a look at this one. Small strong base. Secondary is going to be Zaitsev. Zaitsev E2 elimination. Well, first off, there are two things to note. Beta, beta, alpha. This is the more substituted beta carbon. So it would go that way for Zaitsev. But there are no hydrogens. There are no hydrogens to give up. It can't even go that way. Additionally, for this one, even though it has hydrogens to give up, conjugation. If that double bond were to form here, it would be right next to every single double bond in the benzene ring. Conjugation trumps Zaitsev. So what do I mean by that? Even if you did have a beta hydrogen over there, right? That double bond would still form here. Conjugation trumps Zaitsev. Because it's in such close proximity to those double bonds, it would form there. Even if that hydrogen was perfectly positioned, if it was right there, ready to be taken, it wouldn't happen. It would be a conjugation trumps Zaitsev situation, you know? Now let's take a look at something a little bit harder. Weak base on a Fisher structure. This one sucks. You might look at this and you're like, well, shit. Well, you know, you're not making any double bonds. You're going to keep everything sp3 hybridized because you have a weak base. Secondary leaving group, you're going to have SN2. If I know that my connectivity is going to change the same, everything else I can write the same. Now, here's the real kicker. Whatever stereochemistry this is, it's going to flip. So I know H is going to be over here, and whatever nucleophile I have is going to be over here. Because there's a backside attack, the stereochemistry is going to be reversed. And you can write this any way you want as long as the stereochemistry is right. Flip-flop it, which I would not do because you can't do that with Fisher structures. If you rotate it, draw down there. I don't know why you would do that, but that would still be correct. As long as the stereochemistry is right, you will be fine. But this is the main thing. Stereochemistry is reversed in SN2. Yeah. Whew. Now let's take a look at this. Diels-Alder. All right. We see Diels-Alder. We see an alkene reacting with a diene. Now, the thing is, both the alkene and the diene, they're symmetrical. They're the same deal. We don't have to worry about partial positive or partial negative. We would just have to combine it. Whoops. We'd make that a little bit prettier. CO2, CH3, CO2, CH3. Why am I doing this that way? Well, because these are cis. Because these are cis. Retains stereochemistry. Diels-Alder is a syn addition. It retains the stereochemistry. Now let's look at this. All right. We have a, what do you have it? Small, strong base. Primary. We get an SN2. This one is really easy. It just replaces the bromine. Now let's look at the next one. We have a CH3OH. Solvent equals nucleophile. High temperature, we favor E1. Now, E1 is always going to be Zaitsev. Now, let's take a look. We have our leaving group right here. You might be thinking, hey, I just learned my lesson from one of the previous problems, right? This hydrogen is not antiperiplanar, so it would go this way. But the thing is, that's not true. E1 has a carbocation intermediate. It doesn't need a hydrogen to be antiperiplanar. It just has to be Zaitsev. So again, E1, no antiperiplanar, just Zaitsev. So no matter what, it's going to go this way for E1. Your final product would look like this. If you retain those wedges, I don't think any points would be taken off, but it would technically not be correct because sp2 hybridized carbons like this do not need dashes or wedges. It's just E or Z. If you retain the wedges, again, it would not likely be points taken off, but don't risk it. Okay, let's look at the next one. First step, NaNH2. It's already a triple bond. How the hell can you eliminate it? The thing is, we're not eliminating it. We're ripping off a proton. If you know this, the pKa of ammonium is going to be very, very high. So that's why if you had NH2, it's a very, very strong base, a stronger base than C triple bonded C. So the first step would create CH3, C, this. The first step is going to be an acid base. Okay, it's going to be an acid base. And you, again, from that sodium, you have that spectator ion. So step 2, you have NaCC-CH3. Where do you have it? That's a weak base. And this is going to be a methyl leaving group. That means you have an SN2. So you would get CH3, CC, CH3. A simple substitution. So now let's take a look at the third and last step. H2O, H2SO4, HgSO4. If you have a triple bond and you're acting with this, you're going to create a ketone. So our third and final product, CH, CH2, CH3. If you drew it on the other one, that'll be fine because it's symmetrical. That should be the final and the last bit of this review session, ending at 9:08 p.m. I'm going to stop my share. Nope, I'll probably keep it on. I'm going to stop the recording. See you guys.